Hi everyone, welcome back. In the previous video, we learned how indexes help SQL Server avoid scanning every row. But now the next important question becomes, how do indexes internally work? How can SQL Server navigate to the correct row so quickly, even when tables contain millions of records? The answer is B-trees. B-trees are the internal data structures used by SQL Server indexes, and understanding B-trees is one of the most important steps toward understanding real SQL performance engineering. Now, before we go deeper into the structure itself, there's one interesting question many developers ask. What does the B in B-tree actually mean? Interestingly, there is no officially agreed full form. Over time, different explanations became popular, including balanced tree, Bayer tree, and broad tree. But historically, the most accepted explanation is that the name came from Rudolf Bayer, one of the inventors of the data structure. B-trees were introduced in 1972 by Rudolf Bayer and Edward McCreight, and they were specifically designed for storage systems like databases and file systems where minimizing disk reads is extremely important. Now imagine trying to search one record inside millions of rows. Without a proper structure, SQL Server would need to scan rows sequentially. That becomes extremely expensive. So SQL Server needs a fast navigation mechanism, and that mechanism is the B-tree structure. B-trees reduce unnecessary page reads and allow SQL Server to quickly narrow down where the required data exists. Let's understand this using a very small sales line table. Suppose we have sales IDs from SO-1001 to SO-1007. Now imagine we are searching for SO-1004. The first level of the B-tree is called the root page. This is the entry point into the index structure. The root page does not contain all rows. Instead, it contains ranges and pointers. For example, values less than SO-1004 go left. Values around SO-1004 go center. Larger values go right. So, SQL Server immediately eliminates large portions of data. Next come the intermediate pages. These pages further narrow the search. Instead of checking every row, SQL Server now checks only a smaller subset. This dramatically reduces comparisons and page reads. And importantly, SQL Server is still not touching the actual table rows yet. It is only navigating through the index structure. Finally, we reach the leaf pages. Leaf pages contain indexed values and pointers to actual data rows. For clustered indexes, the leaf level actually contains the data rows themselves. For non-clustered indexes, the leaf pages contain row locators or clustered key references. So once SQL Server reaches the correct leaf page, it can directly access the required row. Now let's follow the actual navigation process. Suppose we search for SO-1004. SQL Server first checks the root page. The root page determines which branch contains the required range. Then, SQL moves into the intermediate page. The intermediate page narrows the search further. Finally, SQL reaches the correct leaf page and finds SO-1004. Notice something important. SQL Server did not scan every row. It navigated through a tree structure. That is why indexes are extremely fast. Now, the behavior of leaf pages changes depending on the index type. In a clustered index, the leaf pages actually contain the real table rows. This means the table data itself becomes the leaf level of the B-tree. And because rows are physically ordered, range queries become extremely efficient. Now compare that with a non-clustered index. In a non-clustered index, the leaf pages do not contain the actual rows. Instead, they contain row pointers or clustered key references. SQL first navigates through the non-clustered index, then jumps to the actual row location. Now let's understand the real power of B-trees. Without indexes, searching is often O(n), meaning more rows means proportionally more work. But with B-trees, search complexity becomes O log n. That means growth becomes logarithmic instead of linear. Even for millions of rows, SQL Server may need only a small number of navigation steps. Now let's connect this back to D365FO. Suppose a sales line table contains 100,000 rows. Without an index, SQL may scan thousands of pages. But with a B-tree index structure, SQL may reach the required row in only around 17 navigation steps. That is a massive reduction in physical I/O. And this is exactly why proper indexing is critical in ERP systems. So the key takeaway from this video is, indexes internally use B-tree structures for navigation. The root page starts the search. Intermediate pages narrow the path. Leaf pages lead to the actual data. And this hierarchical structure is what allows SQL Server to perform extremely fast lookups even on massive datasets. So, I'll see you in the next video.